Hey everybody, we're about to start the assignment 14 material, which is about something called the product and the quotient rules. Let me first give you a little, I don't know, kind of heads up about what's the big picture here. So this starts with a question. How many ways do we have at the moment for constructing new functions out of pre-existing things? If we've got other functions around, what kind of stuff can we do to those functions to get us new options, new functions, but they're somehow related to the old ones. And there's some, oh wait, there's more. It'd really be cool if when we built a new function, we could use our knowledge of the old function's derivative to say something about the new guy's derivative. In other words, we want calculus to play well with the kind of ways we have of constructing new functions from old. So if you've got just a single function laying around, I'll give you a preview. There's one function or two or more functions. But if you just got one function, well, that's the kind of stuff that we've done to get a new function out of the old one. We can do vertical and horizontal shifting, and we can scale vertically and horizontal. You might say we can have reflections both horizontal and vertically, but those are really scale factors of -1. So, these are the basic ones. They just cover the bases. If you've got two or more functions, now there's more stuff that could happen. You could, for instance, take the two functions and add them. And that's really a new function that's created by combining the old guys. Of course, if you can add, you can subtract. So that's a pretty reasonable thing to deal with. You could form the product of two functions. And there's actually an example in economics we're going to look at shortly where that's exactly what you do. Or instead of multiplying, you could divide. You could take one function to the other function's power. And lastly, there's this idea of composition. Feed the output of one function into the input of the other, and sort of take the two of them together and make a chain which does something new. Now let me go through these means of constructing new stuff from old, and mention that in many of them we've already dealt with that. We know how the calculus is going to play out when we say add two functions, right? There's this rule for, I think they called it the sum rule, for what do you do with the derivative of the sum of two things? That's dealt with, and same thing for subtracting. Multiplying and dividing, nah, not yet anyway, but that's actually what we're going to do today. The product and the quotient rules are ways to deal with the derivatives when you've multiplied or divided things. Powers, we're just going to eliminate that. It can be done. There's a process that one can go through, but it's a little involved and it's hard. So we're not covering that in this class. Let me go back to the things where it's a single function. If you do vertical scaling, well, vertical scaling is multiplying on front by a k. And do you remember the constant multiple rule? Vertical scaling and vertical shifting. Actually, shifting is interesting on the derivative. If you just add a constant outside of the function, you've got f of x and then plus k. Well, the derivative of a constant is 0, so there's no effect if you do vertical shifting. If you do vertical scaling, there's still an effect, but it's the obvious one, where the derivative is scaled by the same factor as the function is. Now, horizontal scaling and shifting is tougher, but both of those come in next time when we look at composition. Because remember how horizontal effects were done by an inside change inside the parentheses? That's really a composition with a basic type function. So this is the next time thing, which will handle the horizontal shifting and scaling. So what we're after today is these two things, multiplying and dividing, and how those things affect derivatives. All right, so here we are. This is page 108 in the second book. So remember how there's an oddity in the way page numbering works. If we're in the PDF of this thing, you'll see the page number is 160, but it's numbered as 108 in book 2 of the combined text. Anyway, the first thing in this big yellow box is the product rule. So this tells you how you deal with the derivative of a product. And so what's the product? It's that bit right there. We've got two functions, f and g, and f times g is what you get when you multiply. Now, this looks a little complicated, I suppose, but if you take it in pieces, it's not so bad. What you basically do, at least the way I do it, is you write down fg plus fg, and then you put a prime on the first f, and you put a prime on the second g. That's it. So that's the derivative of f times g plus f times the derivative of g. Let me switch back to the DocCam so that I can point out something. A little note to make here. I've got a couple of little notes to make. One of which is really they should probably be writing f of x times g of x. And then we're taking that whole thing and doing the derivative with respect to x of it. That would be sort of the official way to write this, but they haven't done that. What they've done is drop the of x bits. Those are wrong. And that is perfectly okay to do, so long as there's no chance that there's a loss in communication. So that's called dropping the arguments. The arguments are the inputs to the function, and you don't have to name them. You can just say the thing's f, rather than saying it's f of x. So, and that's why when they write that on the left-hand side, it just looks like d by dx of f times g. Or one way to think of this is, the of x's are still there. We're just doing a shorthand for the moment. Then they switch notations. This is the Leibniz style notation where you're looking at the operation derivative with respect to x applied to the product f and g. And they replace it with the prime notation that's derived from Newton's work, f times g plus f times g prime. It's interesting to notice that when you have the product rule, you could do this in either order. That is, you could say this is g times f prime, and this is f times g prime, or because products doesn't matter, you can change the order in them. You could also say it's f times g prime plus f prime times g. What I'm going to suggest to you is that you not get careless about the order that they're in. Leave things not in these orders, but rather in that one. The first function, the second function, plus the first function, the second function, then prime on the first one, and then prime on the second one. The reason for that is in the next rule we'll look at, the order does matter, and this is the order that you want things in. All right, so let's transition again and take a look at that new thing that I'm talking about. This is called the quotient rule. It's down lower in this big yellow box. And this is how you deal with the derivative of a quotient, of a fraction, f on the top and g in the bottom. So do you see how the numerator of this thing has got the same bits as our product rule did? F prime times g, f times g prime. It's just where that had a plus sign, this one down here has a minus sign. And there's also a g squared in the bottom. Now, that's something we can explain when we get to the next section, and I'll show you where that g squared comes from. But for now, just notice it's the same pattern as the product rule, but turn the plus into a minus and then divide by g squared. Not crazy hard to remember. So, yeah. I want to show you a common misconception. So basically, ignore what I'm about to say in a certain sense, because this is wrong. But still, I want, forewarned is forearmed. I want you to know what not to do when taking a product rule. A lot of people think, okay, I've got f times g, and we're taking the prime of that. So, okay, I'm just just to make myself feel better, I'm gonna write not equal, but it's not f prime times g prime. And it's very easy to see that this is the case that you can't just differentiate the 2 bits when you've got a multiplication thing, because you can put particular things in for f. For instance, what if f and g were both just equal to the identity function? F of x equals x, g of x equals x. What I would be saying is the derivative of x times x should be the derivative of x times the derivative of x, right? That's what I'm saying, but it's not true, because this side, that's x squared's derivative. And x squared prime, we've seen a couple of times, that's 2x. I was about to put the x as a superscript. I don't know, ignore that little dash there. 2x is the derivative of x squared, but what's the derivative of x? 1. And so is the other derivative of x, 1. Right, so that's 1, and this is 2x. They're definitely not coming out the same. So that means that this rule can't be a rule. It's just not right that you just take the prime and put it on both parts. That works great for pluses or minuses, but it doesn't hold for multiplication. So that's one side note. Don't fall for the false product rule idea. One of the things they do in the book is have us verify the product rule in a simple enough scenario where we can go ahead and multiply out the things. So the actual product rule in a non-trivial situation. So the real product rule, fg's derivative is f prime g plus fg prime. Let's look at this in a not too crazy situation, but suppose f of x is x plus 1, and g of x, how about that's x squared minus 1. Why did I pick those two binomials? Well, we could FOIL rule those together and actually do the multiplying, right? We can actually multiply f and g. In fact, let's go ahead and do that. What is f times g? First times first, x times x squared, that gives us an x cubed. Outer times outer would be x squared, inner times inner would be minus x. And last times last is minus 1. Right. So, and there's no like terms that can be combined there, we've just written it out. Fine. What does the product rule tell us? Well, actually, before we push on, let's collect the information we'll need for it. We need to know what f prime looks like. F prime is super easy though, because that's a linear function. F of x is linear, and so you just get the slope, which is 1. And what's g prime? Well, I'm writing g prime of x. I guess both of these I could have dropped the arguments as well. It's 2x, and the minus 1 goes away. It's a constant, right? So you just get 2x. So let's take these a bit at a time. F prime times g, which would be, well, okay, let me write out what we're computing. It's 1 times g, which was x squared minus 1, plus, what's the other one going to be? G prime, which is 2x. I'm messing up. I shouldn't write it that way. I should write it as f times g prime. So f is x plus 1, and then the g prime would go on the end. 2x is back here. I mean, again, this doesn't really matter because this is multiplication and switching order is fine, but I kind of like to keep it in the order that it's in the way we write it down there. Because if you just get used to f prime g plus fg prime, the quotient rule will be less prone to getting messed up. All right, so we can combine some terms and see what else we get. Let's see. Although multiplying by 1 doesn't do much, right? It doesn't do anything. So we get x squared minus 1. Let's distribute this 2x in, and you'll have 2x squared plus 2x. Actually, yeah, there's some things that combine. In both of these, there's a something times x squared. So in the end, you get 3x squared plus 2x and then minus 1. Okay, so that's what the product rule gives us. But the whole point of this bit up here was that we can also just do the prime of this guy. So from here, without using the product rule, we've got that fg prime is what's going to come out of that 3x squared from the first term there, plus 2x minus 1, the derivative of x is 1, and then that's a constant, so it's gone. Yeah, these agree, don't they? That one and this one are the same. Which is a great check, right? If you've got two different approaches you could take to get to the answer, and they agree with one another, it gives you a lot more confidence in what you've done thus far. So, when the book does something similar to that, I think they use different numbers or functions, but they did a similar process of differentiating something both by using the product rule and by multiplying it out and just taking the derivative straightforward. They mentioned that it was only possible to do that because the functions involved were simple, and they said it's generally speaking hard to multiply out two functions. And in fact, it's actually not that bad to multiply at least things like that where they're polynomials. So I think this is a moment for us to show you a technique that extends your algebra abilities just a little bit. At this point, if you're multiplying polynomials, you basically either have a single term thing times some long guy, or things that are both binomials, two terms and times two terms. The FOIL will let you do that. But there is a general method for multiplying polynomials, and it's called the table method. And I'm going to show it to you by example, and then point out that the FOIL method is really just a simple instance of this. So what is the table method? Well, you build a table, as the name implies, and you put in the column and the row headings for this table the terms from the polynomials you're after. So I'm just going to do this by example. Suppose we had x squared plus x minus 1 times x plus 2. If I were doing that, I would make myself a little table. In this case, it's going to be 2 by 3. And I'm going to put the second guy's terms into the row headings. We have an x and a 2. And the first guy's terms into the column headings. This choice doesn't matter. If you switch things, it wouldn't matter. You just get the entries in instead of a 2 by 3 table, it'd be a 3 by 2 table. So that's the setup. The work you do is for each position in here, and I wouldn't normally write these in here, but let's do it for now. You see how you got 6 entries in that table? Each of those is formed by taking the product of the thing on the top and the bottom and the left. So the row heading times the column heading. So x times x squared gives us an x cubed here. X times x, that gives us an x squared there. X times minus 1, that's minus x. 2x squared here, we've got 2x there, and we've got negative 2 there. And then, when you complete the table like this, you just look for anything that's like, meaning they have the same power on x, and combine them. There's only the one x cubed, but see how there's 2x squared and regular x squared? Those two get added together. I'll point out that if there are like terms, they usually happen like as it does in this example, along sort of diagonals. So this product here is x cubed plus 3x squared plus x, because one's minus and one's the 2x is positive, and then minus 2. So it's not really that hard to multiply two polynomials, and in fact, even if it's like 3 terms and 4 terms, it's doable. I would normally turn to GeoGebra and use that expand function I talked about last class. In fact, let's check our work on that just by doing so. Switch over to GeoGebra and see what it tells us here. Get my I haven't started it. So we need actually let's start the CAS calculator. And I want it to expand the same product that we just looked at, which was x to the second plus x minus 1. Oh crap, it does that thing where it leaves it in the exponent. I hate that. X to the second plus x minus 1. That was our first term, right? Yeah. And that's multiplied by x plus 2. Okay, and what it answered with was x cubed plus 3x squared plus x minus 2. I'm just checking back at the other page, and that is indeed what it had there. Cubed, then 3 times the square, then plus x, and then minus 2. So we got it right by hand, and the computer agreed with us, so I'm happy with that. Anyway, if you have a computer handy, then or even a cell phone, because you can use GeoGebra on your cell phone, you can multiply out polynomials. But there's certain scenarios where there's just nothing to be done. You can't. Well, you remember how the like terms combined here? What if we had e to the x and logs and other functions that involved where there's no idea of likeness to put things together? That would create a situation where you just really have to trust the product rule, not try something else. Not try this sort of end run where you just go ahead and multiply and then take the derivative the old-fashioned way. So I did want to illustrate that this is the case, that the FOIL rule is just one case of the table method, which is actually a pretty quick thing. The table method for multiplying x plus 1 times x plus 2 would have us put the terms for x plus 1 in, say, the row headings, and those for x plus 2 in the column headings. And multiplying row and column headings gets us an x squared in that location. That's a 2x right there. This would be an x squared. I'm sorry, just a plain x. 1 times x. And that one would be a 2. And these are, in fact, that's the first times first. Let's see, 2x, that's the 2 times the x, that's the outer. Is plain x, sorry about the scribble on that, that's the inner. And last times last is that guy. Right, so FOIL method or the table method coincide when it's a 2 by 2, but there's no mnemonic like that for doing products of a 3 by 3. A trinomial times a trinomial, for instance, or what I just showed you, a trinomial times a binomial. The table method will work in full generality, even, by the way, for the situation where you're taking a monomial, like how about 3x squared times x plus 1. We would never write out the table for this because, you just distribute this guy across the things. But the table would look like you put the 3x squared in the row headings and you put the x and the 1 in the column headings, and this is distribution, isn't it? 3x cubed there and 3x squared there, and just add them up. So yeah, nobody would do that for sure. I doubt if anybody would bother with a table when you have a binomial times a binomial, so nah. But it is the same. It's the same computation. And the table method works in more generality. So if you're in a tougher situation where you've got a degree 3 polynomial times a degree 4 polynomial, then you need to really, well, either get a computer on the job or do something like this. So next I just want to go through some examples of using both the product and the quotient rule. I guess right from the get-go I'm thinking more about the product rule. And a nice example in microeconomics that the economic theory of a single entity. So not an interactive economy, but just how a single corporation or company operates. So just first, let me mention there are very common letters P and Q that are used as the variables in these kind of micro situations. P for price, Q for probably for quantity, but this is something to watch out for. It's the amount produced, and there's an assumption that's made often that it's also the amount that are sold. That's an assumption. Right? Sometimes you're overproducing, and that means you have to stockpile the goods that you're producing because you're not able to sell them. You should never, no company should be doing that, right? You should set your production schedule to exactly what you can sell. But in the real world, you can't always do that, at least not perfectly. So we're going to usually make this assumption that the amount produced and the amount sold are the same number, but recognize that that's a kind of a fake mathy type assumption that isn't always going to be the case in reality. Now, you should know that full well that there's a relationship between the amount that you sell and the price that you set. And it's usually if you set the price lower, you're going to be able to sell more. And if you set the price too high, well, then you're going to sell less. So that means if you plotted price this way and Q, quantity sold, this way, it should look like that somehow, right? Something where when P is low, Q is high, and when P is low, sorry, said that wrong. When P is high, Q will be low. This turns out to not be 100% the case either. There's this saying, in theory, there's no difference between theory and practice. But in practice, well, what happens sometimes for some unusual goods, particularly luxury goods, you can have this kind of trend up to a point and then have it reverse itself. You set the price too high, even higher, and people go, it must be good, so they buy more of it. Designer handbags are a classic example of that, where one company, I think it was Louis Vuitton, set their price higher and increased their sales, which is quite unusual. So normally we expect this kind of a descending relationship between quantity sold and price. We try to pretend like that scribble isn't there, because that is pretty unusual. This setup means that, and the way I've drawn it anyway, you think of this Q as being a function of P. So rather than just writing Q, you could have written Q of P. For reasons that have never quite been clear to me, economists tend to use this the other way around. They think of it that way, right, with the axes switched, so that the relationship is actually price is a function of Q. Now, for me, that's just weird, so I'm going to write a question mark next to it. It's fine from a mathematical perspective. This is an invertible function, and if Q of P is one function, then P of Q is the inverse function. But what I would normally think a company has control of is what price they set. Right? This is slightly strange. It's saying, what price ought we to set in order to produce a certain demand for our product? And there's an answer to that question, but it's odd. It's not really the thing that we think of having control of. Do we have a control of how many units the public decides to purchase? Not really. But anyway, we'll often use that version of things, P of Q. Price is that as a function of the quantity we intend to sell. Perhaps that's the way to think of it. So the first thing I want to mention is there's a thing called the revenue function, and it's a function of the quantity Q. And, well, what is it? It's how much money you pull in from selling these Q things. And that's Q times the price. And I just talked at length that we can think of the price as being a function of Q. So we've got one function of Q times, well, that's a pretty simple function of Q, but it still is a function of Q. This is a product of two things that are both determined by Q. So if you wanted the derivative of the revenue function, let's see what it would be. R prime, this would mean the Q derivative of it. Well, we'd have the derivative of the first, which is 1, times the second one left alone, that's the price as a function of Q, plus, now we want Q left alone, times the derivative of the price function, P prime. Now, in economics, we often hear the term marginal whatevers. And so let's talk for a second about what marginals mean. Marginals are the things, well, they're essentially the derivatives, but they're the change for doing one more of whatever it is. I already said that, but now I just wrote it down, so I feel like I should repeat it. A marginal is the change associated with increasing, sorry about the funky writing there, I made a stray mark, but the input by 1. So it could mean, for instance, if you were thinking about how is our profit associated to our advertising budget, the marginal would be, well, how does the profit change if we spend $1 more on advertising? The way I'm talking about it here, the marginal would be, how do things change if instead of making, 2 million cars a day, we make 2,000,001 cars a day? That probably can't make that, nobody makes that many cars a day, but you get the idea. Changing the production level from Q to Q plus 1. That's a marginal, and it's really this very close to the same idea as the derivative. In fact, most often we basically, if we want a marginal, we don't bother thinking about the change, figuring out the change from changing the input by 1. We just report the derivative. Usually just use the derivative. If you've got somebody that's really fussy about it, sure, you can figure out what your revenue is at 1,000 units, and then figure out what the revenue is at 1,001 units, and then do the subtraction, and that's fine. But usually just use the derivative because it's quicker, and it'll only be off in the third or fourth decimal place. So what this is telling us is that the marginal revenue is the price function plus Q times the derivative of the price function. That's something, and that's an actual rule that people will use quite often. The derivative of the revenue function is the same thing, or close enough to the same thing as the marginal, and we've got a formula for the derivative. So there you are. Now, another place where some of the rules we've learned pops up in this microeconomic setting is thinking about the profit function. The profit function for a particular productivity level, P of Q, is, well, you take all your revenues at that production level, and you subtract out your costs at that production level. So revenues minus costs gives you profit. Well, what do we got here? A subtraction of two functions. Remember how we had a rule for dealing with subtraction? This is another place where it can be applied. CQ is interesting in its own right because this is usually divided up into 2 bits. There's what are known as fixed and variable costs. Often we think of CQ as being a linear function. That is, you've got a fixed amount, costs that are associated with just keeping the doors open, the rent on the building you're in, and the electricity bills, things like that. And then there's variable stuff. If you're producing something that's made out of steel, then you've got to buy a certain amount of steel for each item you produce. So that cost depends on how many units you're producing. So usually we think, well, the fixed numbers we can't change. The variable numbers are more or less set on a per unit basis, but there's some wiggle room there. Sometimes this isn't just a linear thing. The variable things may be influenced by economies of scale, where when you have a lot of productivity, your suppliers will sell you the things at a better deal, at a discount, because they're selling you 1,000 things a day rather than 10. So increasing productivity may get you better deals on your variable costs, and that means this isn't necessarily a straight line. All right. Well, I'm not going to go through a particular example of that. There's plenty of that in the homework and in the assignment. But I think that brings us to a good stopping place. So I think I'll say good day to you for now. Have a good rest of yours.